We're only speaking for a very short period of time, but I think I've got twice as long as everyone else, and I've got 10 minutes. So, thanks, Mike. I'm talking about the role of agroforests in climate change mitigation, so I'm going to have to talk very quickly to explain that. And the short story is this little pictogram shows an overview of the global carbon cycle. Each box represents one of the major stocks of carbon in the global carbon cycle, and the arrows represent the flows or fluxes of carbon in between those boxes. And the numbers are in billions of tonnes of carbon, what we call gigatons. So you can see in fossil fuel box on the bottom right, there's somewhere between 5 to 10,000 gigatons. In the oceans, there's carbon in what the ocean's kind of broken up into shallow and deep ocean. There's about 700 gigatons in the shallow, 37,000 in the deep ocean. It's a very interesting story, very important story, which we've got time to talk about where that carbon came from. On land, roughly, there's maybe 2,000 gigatons, and there's currently about 780 in the atmosphere. And those arrows are all natural flows. There's natural exchanges of carbon between the land ecosystems and the atmosphere, and between the oceans and the atmosphere. These are natural processes. But that arrow between the fossil fuel carbon and the atmosphere is artificial. In the absence of humans mining and burning fossil fuel, that arrow would not exist. So the major problem we've got in climate change is that we're mining and burning fossil fuel, and some people think that it has been suggested that that's not a very significant amount compared to other natural processes like volcanoes. This is not true. To get as much, there's about maybe 7 gigaton of carbon a year going into the atmosphere from burning fossil fuel. That's the equivalent of 3,500 Mount Helens every year. So when people say, oh, you know, it's nothing more important than a volcano, volcanoes emit more, degas more CO2, it's not true. That's the major problem. But there's a second problem, and it's kind of related, where we're destroying the world's terrestrial ecosystems and oxidising those carbon stocks. And we've already destroyed about half the world's forests, and there's about 50% less, plus there's carbon in other ecosystems. So, if you like, we've got two problems. We are mining and burning fossil fuel and creating a completely artificial flow of carbon into the atmosphere, and we're destroying and degrading ecosystems, depleting those carbon stocks, and accelerating what is, if you like, a natural flow. So there's an accelerated natural flow of the stock of carbon in ecosystems plus the fossil fuel carbon. We've got two problems we've got to fix. How do we stop using fossil fuel carbon, and how can we avoid emissions from deforestation and degradation, and where possible, replenish those depleted carbon stocks? Now, replenishing the depleted carbon stocks is possible up to a point, because a lot of the world's forests have been cleared and are continuing to be degraded for food production, and we're heading to having 10 billion people on the planet by 2050. But anyway, that's the challenge that we have. So I say here that ecosystems provide an important buffering role in the natural global carbon cycle. The aggregate stock of carbon they store is about 3 times the amount that's in the atmosphere. So it's a lot. So if we continue to deforest and degrade forests and other kinds of terrestrial ecosystems, there's a lot of CO2 that will end up in the atmosphere. In addition to the carbon we're burning we're emitting from fossil fuel. This graph is a bit complicated, as all graphs are, but it basically shows on the left-hand side, we've got time along the bottom, CO2, total CO2 emissions since 1960. What's really important here is the fraction of that CO2 that's staying in the atmosphere. Because I mentioned on the other diagram, CO2 naturally exchanges between ecosystems and the atmosphere and the ocean and the atmosphere. It's natural processes. But we're making the problem worse faster than it can be fixed. More CO2 is going up into the atmosphere, the natural processes can draw it down. So the fraction of the CO2 that's staying in the atmosphere is increasing through time. And again, this is showing CO2 emissions on the top axis and time on the bottom back to 1960. the amount of fossil fuel carbon we're using is drastically increasing. Emissions from land use change are remaining about the same. They're somewhere between 10 to 20%, and they remain at 10 to 20%. So there's a significant slug of the fraction of CO2 that's staying up in the atmosphere and building up over time. Let me say very quickly that one of the problems we've had in the international dialogue is that the legal definitions of forest under the Climate Change Treaty don't recognise the difference between a natural forest and a plantation forest. And this has led to a lot of the confusion that we heard from that news report earlier on. Natural forests have biodiversity, they've got genetic diversity, species diversity, ecosystem diversity. This gives them what we call ecosystem resilience and an adaptive capacity. This means they have longer lived, larger and more stable and reliable carbon stocks compared to industrial production forests and plantation forests, which are much shorter lived and have much less dense carbon stocks. Where is the carbon in a forest? Well, I argue we should be talking about total ecosystem carbon. Of course, there's this diagram illustrates, and I don't have time to talk about it. It's a dynamic system, but we have carbon in the living biomass, the trees, and below ground in the roots. We have carbon in the dead biomass on the ground, and the standing dead biomass, and in the soil. So it's not just about the amount of carbon that's in the usable stem of a tree. It's about the carbon that's in the whole system, the total ecosystem carbon. And we have a lot of it. Here's one estimate. We might have about 23 billion tonnes of it in all our different ecosystem types. Interestingly, this table shows the countries ranked by the amount of forest they have, and you'll see that Australia is the 7th most forested nation on Earth. And if you look at our other kind of ecosystems, other woody ecosystems, shrublands, we're the most other wooded land. And when you put it together, we're certainly top 10. So ecosystem carbon, we have a lot of it, and it's significant, globally. And as you heard, our forests are particularly dense. They're not all the most dense on Earth. They range naturally depending upon site conditions and climate and geology. But certainly land use history is a big factor. But our tall wet forests are certainly amongst the most carbon dense on the planet for a number of reasons. Eucalypt trees are very dense, they live for a very long age, and we have our cool temperate and subtropical forests, because they're cooler and wetter, the biomass grades more slowly. So just to cut to the chase about land use impacts on forests, the point was made in the video that when we deforest, we effectively create a non-forfeitable carbon debt, which takes a long time to repay. The woody biomass can take centuries to repay. The soil carbon stocks might take longer. There's a lot of uncertainty about soil carbon. I say it's non-forfeitable because Earth is a closed system when it comes to carbon. The carbon doesn't leak out into outer space. Right? It's got to go somewhere. It's got to go into the ocean, or it's exchanged between the ocean and the atmosphere, but it doesn't disappear. It has to be accounted for. And similarly, another complex graph, when we put a forest under a commercial logging regime, essentially what we do is we shift the age structure of the forest to younger trees, and the younger trees store less carbon. And that's the simple message there. So essentially, industrial logging cycles deplete the standing ecosystem carbon stocks, create a carbon debt, and the standing stock of carbon is, if you like, permanently shrunk. And I will end now by just noting that carbon is not the only value a forest has, and we have to be very careful not to adopt a purely reductionist argument where we strip all the other values away. Because when we talk about carbon in an ecosystem context, that carbon cannot be distinguished from everything else. It cannot be, it cannot be extracted from all the other values that we have in a forest, the role they play in regulating fresh water, local climate, wildlife habitat, etc., etc. Thank you.